this is a summary of all the algorithms that we've discussed, right? There are a couple of algorithms here that we have not yet discussed. All reduce chain we have not discussed, right? So I'll just highlight this. So just ignore this for the time being. Okay? Just ignore this entry. So we've discussed all the other algorithms. Okay, and I've just summarized this in a table over here. Okay? So let's try to understand how good are these algorithms. So what we are going to do is, we are going to see what are the lower bounds for communication using the Hockney model. Right? So we are discussing Hockney model only. So what are the lower bounds? So let me park broadcast for a minute, right? We'll come back to this. While we are looking at lower bounds, I'm only going to talk about large messages. So let me assume that I have very large messages that I want to communicate, right? M is very large, right? So under that assumption, I can basically ignore TS, right? And I'm just going to concentrate on the term TW, okay? So let's start with scatter. Can we come up with a lower bound for scatter? Can I argue that this is the minimum time it's going to take to do scatter? So the argument is quite simple, okay? The node that has all the data has to send out all that data. I mean, you can't do faster than that, right? It has to send out that data, and how long is it going to take for it to send out the data? So how much data does it have? MP, right? That's the data it has. And when you're doing reduce scatter, how much of this data do I have to send out to the other nodes? Part of this is going to eventually be accumulated on my node, on the same node, right? That's nothing but M. M amount of data is going to be accumulated on this node. So how much data does it need to transmit? M times P minus 1 is the data that it has to send. There's no other way, right? Because finally that data has to reside on other nodes, right? So M times P minus 1 times TW is a lower bound. And do we have algorithms which achieve that? So if you see the ring algorithm, the mesh algorithm, the hypercube algorithm, recursive doubling does not achieve that. Okay, so just carefully look over here. You have to note that recursive doubling does not always give you the optimal algorithm, right? And as a matter of fact, asymptotically we have the optimal algorithms for reduce scatter on different architectures, ring, mesh, hypercube. Okay. What's next? Let's look at scatter. What are we looking at right now? Reduce scatter or scatter? Okay, the argument is the same for scatter and reduce scatter, right? You have MP elements and you have to send out M times P minus 1 elements, right? So for both scatter and reduce scatter, the same bound applies, so same lower bound, and we have algorithms which are optimal. Okay? Remember, this is only for large messages. For short messages, these are not the optimal algorithm. You would rather use recursive doubling or something, right? Because look at the cost associated with TS. It is high in these algorithms, right? Other than hypercube. But if you look at the recursive doubling, the cost associated with TS is only log P, order log P, right? So for short messages, you prefer recursive doubling. For large messages, these algorithms will give you the optimal result, okay?
So for short messages, do we care for the complexity? Like any day it's going to be this?
No, we do care about the complexity. Because you may not be doing a lot of computations on a node, but maybe you just want to periodically check whether the computation across all the nodes has finished or not, so you're exchanging a flag. But that communication is going to cost you, because when we're talking about hundreds of thousands of nodes, the time it takes for one data to reach the other end is quite large, right? Maybe all you're doing in the actual computation is adding one element, right, which takes no time at all. But the communication of just exchanging the information whether you're done or not is taking very long.
These TS and TW values?
TS would be very large in that case, right? The startup time would be very large, because we are accounting for the latency, the code execution, all those things in TS. TW is only accounting for the bandwidth. So there we are interested in how long it takes to send the entire message on the link. Okay. All right, let's look at all reduce. Do we have a lower bound for all reduce? What is the total amount of data on every node? There is M data. So what is the lower bound I can get for all reduce? So everybody has data M. everybody needs all my data in order to have the summation of all the elements. I need to send all my data out of me, right? Node 0 needs to send all its data because node 1 needs to sum up all the data, but to sum up all the data, it needs all the data from node 0. So node 0 has to, at some point or the other, maybe it will send partial sums and full sums, but all the elements have to be sent out at least once, right? So you need to send out at least m data, right? So m times tw would be a lower bound. Do I achieve that? Look at the all reduce algorithms. So this is recursive doubling for all reduce. So how do you get recursive doubling algorithm for all reduce? Well, we've already discussed all reduce is nothing but reduce followed by a broadcast, right? So the cost of reduce is ts plus mtw log p. We've already seen that, right? It comes from here. And the cost of reduce and broadcast both is the same, so it will be 2 times that, right? So that is the recursive doubling algorithm for all reduce, okay? So does it achieve that? No, there's a factor of log p over here. Does the hypercube algorithm achieve that? No, there's a log p factor over here, okay? So we don't end up achieving that. Okay, so we don't end up achieving that in all reduce. All to all, what is a lower bound, right? So we need to argue for a lower bound. What about broadcast? Again, broadcast, I can argue that all the data needs to be sent out. That's all I can argue, right? So again, m times tw is a lower bound. What is the cost associated over here with broadcast? M times tw times log p. Again, it's not optimal. So let's just mark this. We already have optimal algorithms for scatter, reduce scatter. All to all, let's discuss later, right? Broadcast and all reduce. Either I need to improve my lower bounds somehow, or I need to design better algorithms, okay? And similarly for all to all, I don't know what is the best, right? Again, the simplest I can come up with is mtw for all to all, yeah? Is that the best? We don't know. There's a gap over here. So how do I fill the gap? Either I get a better lower bound or I improve the algorithm, okay? So this is what we'll discuss next time.